Hello, my name is Christopher Henriksen, and today we'll be going over population genetics, the Hardy-Weinberg equilibrium, and how directional selection can violate the Hardy-Weinberg equilibrium. And we will be doing that using this, which is Vampire Island. This is a scenario where vampires do exist, and society has decided to put all the vampires on one island with no humans, and there's some animal and some deer and things like that, but no humans. So we have three different types of vampires. Vampires that prefer non-human blood, big A, big A. Vampires that can subsist on either human or non-human blood, big A, little a. And little a are vampires that prefer human blood. Now, before any kind of mating has occurred, we have this collection of individuals. The first thing we're going to want to do is calculate the initial allele frequencies. Please pause here and check out my math on how to do it. But this actually ends up getting us a gametic array of 0.6 big A, 0.4 little a, which we can then use to calculate the genotypic frequencies in the Hardy-Weinberg equilibrium. Pause here and check out the math, but we end up getting a genotypic array of this. And this is important because notice that all of this adds up to 1, which is consistent with the Hardy-Weinberg equilibrium. Now, after selection occurs, we have different fitness levels for the different vampires. Of course, the vampires that can subsist on non-human blood have the highest fitness, as there are no humans on the island. The vampires that can eat humans or non-human blood, they do relatively well, but they have a lower fitness. And the vampires that prefer human blood, they don't have a lot to eat on this island. Pause the video here and check out the math. But this ends up getting us a genotypic array of this, and this is our genotypic array after selection, which we use calculating we had to use the average fitness to get, because the unadjusted survivors do not equal to 1, and that is not consistent with Hardy-Weinberg, so we have to do some mathematical finagling to get it back in sync. Anyway, after that, we calculate the allele frequencies after selection using our genotypic array. So pause here if you'd like to see the math worked out for that. And we actually end up getting a gametic array of this after selection. As you can see, there are more big A alleles than there were in the first gametic array, which gives us a good hint that as time goes on and after rounds of successive mating, we will see that this population will shift towards the big A, as in we will have more big A alleles in the population, as the big A alleles have the highest fitness, as the vampires that prefer non-human blood are the most likely to survive, as there are no humans to feed on.